In the last lecture, we discussed about the representation of signals as a linear combination of complex exponentials, and we saw what the motivation for doing so is, and we showed that uh, complex exponential signals are eigenfunctions of LTI systems, in the sense that if a complex exponential signal is applied as input to an LTI system, then the output is also a complex exponential signal scaled by some factor which is called as the eigenvalue of that system, right? And then we also talked about the representation of a signal as a linear combination of harmonically related complex exponentials. Okay, initially we talked about representing a signal as a linear combination of complex exponentials, but later on we imposed a condition that the complex exponentials have frequencies which are harmonically related to some fundamental frequency component which we call as omega naught. And based on that, we talked about, we gave some definitions like what is the fundamental frequency component, which is also called as the first harmonic, and then the component which is having twice the fundamental frequency is called as the second harmonic. If the component has 3 times the fundamental frequency, it's called the third harmonic. And in general, if it is n times the fundamental frequency, we call it as the nth harmonic of the signal. Now, so when we are able to represent a signal as a linear combination of harmonically related complex exponentials, we call such a representation as the Fourier series representation of the signal. And today we'll take that discussion further, and we'll do an example of representing a signal in terms of its Fourier series. And I will also be showing the graphical depiction of the individual components of that signal, which are added up to produce that signal x of t. Okay, so we've taken this example here where the fundamental frequency omega naught is fixed as 2 pi, and the signal is having these 7 frequency components, 7 components going from k equal to -3 to +3. So we want to look at this signal, look at each of these components, and see that when we add up all those components, we get the signal x of t. Now, in this particular example, the values of ak, that is a0, a1, a2, a3, have been provided to us. Okay, normally when we are doing the Fourier analysis, we have to compute these values, and how to compute these values, we will talk about that later towards the latter part of today's lecture. But let's, for the sake of understanding and appreciating what is going on here, when we represent a signal in terms of the Fourier series, these values have been given to us. Okay, so we have a0, a1, and a minus 1 are given as 1 by 4. A1 and a2 and a minus 2 have the same value, and a3 and a minus 3 also have the same value. Okay, so these are given to us. So what we do now is we'll first break down the summation for each value of k. So we have values from -3 to +3. So in the middle we have 0. So I'm just going to put those numbers. So we have from -3, -2, -1, 0, 1, 2, and 3, right? So the term corresponding to k equal to 0, I've written as I've written it first here. So that's a0 e power j into 0 into 2 pi t. So that's e power 0 into a0, which is a0 into 1, that is a0. So the term corresponding to k equal to 0, I've written it first here. And then the terms corresponding to a equal to 1 and -1, right? So we will have for k equal to 1 and -1, it will be a1 e power j 2 pi t, and for k equal to -1, it will be a -1 e power j minus 2 pi t, right? So that minus I put in front here. So because we combine these terms together, okay, now we have a1 and a -1, because e power j 2 pi t and e power minus j 2 pi t, they have the same frequency omega, which is 2 pi, right? So we combine these two terms together. Similarly, when k equal to 2 and -2, we get a2 e power j 2 into 2 pi, which is 4 pi t, and similarly for minus 2 it is a minus 2 e power minus j 4 pi t. Again, e power j 4 pi t and e power minus j 4 pi t are complex conjugates of each other, and they have the same frequency, which is 2 times 2 pi, which is 4 pi. And the last components we have is for 3 and minus 3, so that gives us a3 e power j 6 pi t and a minus 3 e power minus j 6 pi t. Okay, so we have our terms here. For basically we've just opened up the summation and written down all the terms involved in that summation. So next thing we want to do is we will substitute the values of the AKs that are being provided to us, and see what happens. So our x of t is 1 plus a1 e power j2 pi t plus a minus 1 e power minus j2 pi t, and since a1 is equal to a minus 1, both are 1 by 4. That 1 by 4 has been taken out as a common term here. Similarly for a2, since a2 is equal to a minus 2 and they are both equal to half, that half term has been taken out as a common factor here. And similarly for a3 and a minus 3, they both have the value of 1 by 3, which has been taken out of the brackets here. Okay, so now we have these signals which we can which are of the form e power j theta plus e power minus j theta, right, which is nothing but 2 cosine theta. Okay, since by the Euler's formula, cosine theta is e power j theta plus e power minus j theta by 2, and since the divide by 2 is not there, so we have it is 2 times cosine theta. So theta in our case here is 2 pi t. So we have 1 plus 1 by 4, 2 cosine 2 pi t, so that's for that term. So here e power j 4 pi t plus e power minus j 4 pi t is 2 cosine 4 pi t, and similarly for the 6 pi t term we have 2 cosine 6 pi t. Okay, now we simplify this and we get this final expression where we have the x of t consisting of a term of 1 cosine 0, that's the 0 frequency term. That's the fundamental frequency term, having a frequency 2 omega. That's cosine omega t. Omega is 2 pi. That corresponds to the omega naught that we have defined here as 2 pi. So that is basically our fundamental frequency term, or it's called as the first harmonic term of x of t. This is cosine 2 into 2 pi t, which is cosine 2 omega naught t. So that is the second harmonic term, and that term here that we have is the third harmonic term, which is 3 into 2 pi t, right? 3 into 2 pi is 6 pi. So this signal x of t is the sum of 4 frequency components, which is 0 frequency, a frequency of omega equal to 2 pi, omega equal to 4 pi, and omega equal to 6 pi. Now each of these frequency components has a different amplitude. So the 2 pi frequency term has an amplitude of half, the 4 pi frequency term has an amplitude of 1, and the 6 pi frequency term has an amplitude of 2 by 3. So the idea that we are developing is basically to split the signal into its individual frequency terms, and also to identify what is the amplitude of each of those frequency terms. So we have identified now that for this particular signal x of t, it is a sum or combination of a term which is 0 frequency, that is 1 cosine 0 t. 0 is cosine 0 is 1, so 1 into 1 will become 1. So when there's nothing written here, that corresponds to the 0 frequency term. That is the fundamental frequency term, as I said earlier. That is the second harmonic, and that's the third harmonic. So we have been able to represent the signal as a sum of cosine waves in this particular case. Okay, now this is a special case where we have all the coefficients AKs, okay, A0, A1, A2, A3, and A minus 1, A minus 2, A minus 3. All of them are real numbers, okay? But that need not be the case. This is a simple example only for illustration purposes, where we have chosen the values of all the AKs to be real numbers. But in analysis, we might end up with the values of AKs which are complex numbers as well, as we will see later. So now let's try to look at these individual components and see what happens if we add them one by one. So what we have here is our the x of t signal. Okay, the signal x of t, which is the sum of all those four frequency components, which is the 0 frequency component, 2 pi, 4 pi, and 6 pi. When we add all of them together, this is the waveform or signal that we get for x of t. Now we are going to take up each of these components, okay, which is the 0 frequency component, which has an amplitude of 1. So that's a 0 frequency having an amplitude of 1. So that's the 1 component. And then we have the cosine 2 pi t, with an amplitude at half. So the peak amplitude here, if you see, it's half. So that's 0, that's 1, it's halfway there. So that's a peak amplitude of 0.5. Now if we add these two components, basically we are adding a DC shift to this waveform. So this waveform is going to get shifted up by 1. So instead of being centered on 0, it is now going to be shifted up and be centered on 1. You see, notice here. So when we add these two waveforms, 1 plus half cosine 2 pi t, that means we have added only the first two terms of this synthesizing equation. What we get is this cosine waveform shifted up by 1. So instead of being centered on 0, it is now centered on 1. So it is a vertical shift upward by 1 volt. So now the peak value from 0.5, it has gone to 1.5. Okay. So we've added two terms. Now what we'll do is we'll add three terms and see what it looks like. So we'll add 1 plus half cosine 2 pi t plus cosine 4 pi t. So when we add the third term as well to this, what do we get? So when we add three terms of this, three components of this equation, then we get the waveform which looks like this. But this is still not the same as our x of t. If you notice x of t, it has these oscillations here in the smaller oscillation as well, but here you don't see those small oscillations over here. So now it is still not the full x of t because there's still one more term that needs to be added. So now with three terms added, we are getting closer to our x of t, but it is still not yet x of t. So we'll add the fourth term as well. So once we add all the four components, we get our signal x of t, which is the sum of those four components. And what is important to note here is that when we're doing the Fourier analysis, we are trying to find out what are the frequency components present in the signal, and also we need to find out what is the amplitude of each of those frequency components. So for example, the 0 frequency component has an amplitude of 1 in this case. The 2 pi frequency component has an amplitude of 0.5, which is half. The 4 pi frequency component has an amplitude of 1, and the 6 pi component has an amplitude of 2 by 3. So we need to add the correct frequency components with their correct amplitudes together to get our signal x of t. So we have represented our signal in terms of these cosine waveforms, which in turn can be represented in terms of the complex exponential signals. So you see, it's basically this x of t has been represented in terms of the complex exponential signals. So as I said earlier, the values of the Fourier series coefficients, which are ak, were given to us in this particular example just for the purpose of understanding what is exactly happening when we are doing the Fourier series and what it means, what the summation term means. Okay, but in practice, what we will have to do is, if we are given a signal, we will have to compute the values of the AKs. Okay, all the values of AKs, that is A0, A1, A2, A3, and A minus 1, A minus 2, A minus 3, A minus 4, and so on and so forth, depending on how many values are necessary to represent the signal. All the AKs have to be computed. And these values of AKs, okay, the set of coefficients, which we denote as AKs, they are called as the Fourier series coefficients of the signal x of t. Okay, these are called as the Fourier series coefficients. And what information do these coefficients represent? These coefficients tell us what is the amount of each frequency component or each harmonic is present in the signal. So as we saw earlier, the frequency component of 2 pi is having a contribution of 0.5 volt towards the signal. The frequency component of 4 pi is having a contribution of 1 volt towards the overall signal, and so on. So the Fourier coefficients tell us the measure of each of the harmonic components that are present in the signal x of t. Okay, that is what they tell us. And the AKs are basically our Fourier series coefficients, which we have to compute. Of course, how to compute that, we will come to that later. Okay, but you need to understand first of all what they represent. Okay, so the next thing we want to discuss is how do we compute the values of these Fourier series coefficients. Okay, the equation or the formula to compute the values of AKs is given by the following equation, which is each of these AK is 1 by t integral over one period, where t is the period of the signal. Okay, 1 by t integral x of t e power minus j k omega naught t. So for a0, this will become 1 by t x of t e power j into 0 omega naught t, so e power 0. That is simply integral of x of t over one period. For a1, we'll put k equal to 1. For a2, that is for k equal to 2, we'll put k equal to 2 in this exponent as well. And for k equal to 3, we'll put k equal to 3 in this exponential here, and so on, and we'll compute this integral, and that will give us the values of each of the AKs. And this equation that we have here is called as the analysis equation. Okay, previously we talked about the synthesis equation, where we represent a signal as a summation or linear combination of complex exponential signals, and we call this as the synthesis equation in the previous lecture. Now the formula or the equation that is used to compute each of these AKs, okay, that is given in this red box here. This equation is called as the analysis equation. Okay, and what we have on the right hand side here is basically we have replaced omega naught as 2 pi by t. Okay, because omega naught is equal to 2 pi by t, so that is what we have done here. So you can just write it as omega naught as well. So this is called as the analysis equation, and what we have at the bottom here, that is the synthesis equation that we have seen in the last lecture as well. And this is basically the synthesis equation is what is called as the Fourier series of the signal x of t. And because we have this in terms of the complex exponential, we call it as the exponential Fourier series. So now let us look at the analysis equation a bit deeper and try to understand in particular what does the Fourier series coefficient corresponding to k equal to 0 represent. Okay, so the analysis equation, which is given by this is how we compute the values of AKs. So for each value of k, we put the corresponding k value here in this exponential and compute this integral. Now this integral is over one period t. Now if the signal is periodic with a certain period, we can choose any period within the signal. So for example, if we have a sinusoidal waveform with the period of 2 pi, we can make this integration from 0 to 2 pi or from minus pi to pi. So we choose the limits of the integration such that it covers one complete period of the signal. Okay, which period, that does not matter. Any one complete period of the signal would give us the same information. So we need to just integrate over any one period of the signal to get this value of AK. Okay, so that's our way of computing the AKs. And when k equal to 0, this exponential term e power 0 becomes 1. So what we have here is 1 by t integral x of t over one period, which is basically the average value of x of t over one period. The average value of the signal over a period is nothing but its DC level. So it's basically, if we had to go back at the, okay, so if we have this cosine waveform from this peak to this peak, that's one period. Okay, now the average value of the signal in one period, if you notice, is going to be 0. That is why it is centered on 0. But if it is shifted up or down, then the average value would be different. For example, here, this particular waveform, the average value is going to be 1, because if you integrated it over one period from this peak to this peak, then the average value will turn out to be 1. As you can see that this waveform is centered on 1. So the term corresponding to k equal to 0 is basically giving us the DC level or the DC component of the signal. So what we have seen till now is the exponential Fourier series, wherein the signal is represented in terms of the complex exponential. And there are other forms of representing the signal, other forms or variants of the Fourier series, which can be extracted from the exponential Fourier series. So if we write down the exponential Fourier series and simplify the terms and impose certain conditions, and under those conditions we get different forms of the Fourier series, and we will see one such useful form which we will encounter in a lot of our exercises, and that is called as the Sine-cosine form of the Fourier series. Basically, we will have the Fourier series or the signal represented in terms of cosine terms and sine terms. So how do we get that? So for that, we'll start with the consideration that our signal x of t is a real signal. That means it is not a complex signal. A complex signal, on the other hand, will have a real part and an imaginary part. Now we are talking about a signal x of t, which is a real signal, where that means the imaginary part of the signal is 0. So it's like a plus j times b. So the b is 0, so it's simply a real part. Only the real part is non-zero. So for a real signal, the complex conjugate is the same as the original signal, right? So for example, if we have a plus jb, the complex conjugate is a minus jb. So when b is 0, a plus jb is simply a, and a minus jb is also a, right? So for the real signal, we have the complex conjugate x star of t, that denotes the conjugate of the signal x of t, is equal to the original the signal x of t itself. So basically what we're going to do is we are going to write the representation in terms of the complex conjugate, and we'll get some information or relationship between the ak and a minus k, okay, because we have these coefficients ak's for positive values of k as well as negative values of k. So we want to try to get some information or relationship between them. So to do that, we are first of all recognizing the fact that the complex conjugate of a real signal is the signal itself. So since our Fourier series representation is given as this, the complex conjugate means we have to take the conjugate of all the terms in the summation. So for ak, the conjugate will be ak star, and for e power j k omega naught t, the complex conjugate is e power minus j k omega naught t. So that's something you are familiar with, right? And that should be equal to the original signal x of t itself, because x star of t is equal to x of t. So that is x star of t, which is the complex conjugate of x of t, and that is equal to our signal x of t, because x of t is a real signal. Now we will simply replace k with minus k, because k is going from minus infinity to plus infinity. We are just reordering the terms. We are doing the positive, going from minus infinity to plus infinity. It is like going from infinity to minus infinity in the summation. So when you add things, it doesn't matter in which order you're adding. So we just replace k with minus k in this equation and see what happens. So when we put in place of k as minus k, we have a k star becomes a minus k star, and e power minus j k omega naught t becomes e power plus j, because minus j, k becomes minus k, minus into minus becomes plus. So we'll have this term, okay? So that means the complex conjugate, okay, that we put here is the same as the original signal x of t, and for these two equations to be the same, right, because this is also x of t, and this term is x of t, and this term is also representing x of t. They are both equal. So therefore, for these two to be equal, it implies that this a minus k star is equal to ak, right? So only then these two are identical, right? Only then these two equations are meaningful, because both, we say, are representing x of t. So that is only possible if this a minus k star is equal to ak. That means the complex conjugate of a minus k is ak, and hence the complex conjugate of ak is a minus k, right? So it's like if we have 2 plus 3j, for example, its complex conjugate is 2 minus 3j. So if 2 minus 3j is the complex conjugate of 2 plus 3j, then 2 plus 3j is the complex conjugate of 2 minus 3j. So what we're basically saying here is that ak and a minus k star are conjugates of each other, or in other words, ak and a minus k are complex conjugates of each other. Okay, that's what we're trying to say here. Now if these ak's happen to be real numbers, okay, if ak is a real number, then ak will become equal to minus ak, as we have seen in the previous example where we had a0 as 1, a1 and a minus 1 as 1 by 4. So a1 and a minus 1 were same, and a2 was equal to a minus 2, and that is going to be true when the ak's are real numbers. So for example, if this complex if this imaginary part was 0, then ak and a minus k would be the same, right? So that's one part of information that you need to bear in mind, which will be useful when computing the Fourier series coefficients. Okay, now with this information we can proceed to simplify the representation of this x of t. So what we get is this summation, which we have now split into three parts. It's from summation from minus infinity to infinity. Now we have broken this down into three segments. So from minus infinity to minus 1, and then for k equal to 0, and then for k equal to 1 to infinity, right? So we just split this range into three sub-ranges. So that is from minus infinity to 1, 0 we've kept separately, and 1 to infinity. So now what we do is we just reverse the order of the summation. From instead of going from minus infinity to minus 1, we put it as 1 to infinity and change k to minus k, right? So this is exactly what we did earlier as well when we replaced k with minus k. So we have changed k to minus k, and similarly k here has become minus k, so we put the minus in front now, and we've changed the summation limits. That is, instead of from minus infinity to minus 1, it is now from 1 to infinity, and the a0 term becomes a0 into 1, which is a0, and we have this term which is from 1 to infinity, right? Now we can combine these two because they have the same limits of summation. So we can combine these two terms and put it under the same summation. So we put a0 here, and we have this term which is here, and the a minus k term we bring it here. Okay, and the next thing we do in this simplification is that we use Euler's relationship to write e power j k omega naught t as cosine k omega naught t plus j sine k omega naught t. So e power j theta is cosine theta plus j sine theta, right? So we just use that identity to write down in this form. So it's ak into the cosine plus j sine k omega naught t. Similarly for here, e power minus j theta is cosine theta minus j sine theta, right? It's in that form. So we have this. So we put all of this under the same summation, and we just combine the like terms, okay, and put them together. So we bring all the cosine terms together, the real parts, and all the j sine terms together, that is the imaginary parts of these complex numbers. So taking all the cosine terms together, we will get we can take the cosine as a common factor. So we have ak plus a minus k multiplying with the cosine term, right? So they both so we can take the cosine as a common factor here. And similarly, we can take the sine k omega naught t as a common factor here, which is getting multiplied with jak. So we've taken j common, and ak minus a minus k, right? Okay. Well, that's a simple algebra which you can follow. So basically, now we have our signal x of t as a0 plus the summation. Now what we do is we take this small ak plus small a subscript minus k and call it as a capital A sub k. Okay, so that's capital A k cosine k omega naught t plus capital BK sine k omega naught t. Now the capital AK is the small ak plus small a minus k, and the capital BK is this term, which is j times small ak minus small a sub minus k. Okay, so we just represented these introduced these new terms here, which are obtained from our existing terms ak and a minus k. Okay, so ak, capital AK is the sum of small ak and small a minus k, and capital BK is the difference between small ak and small a minus k multiplied with j. Okay, so we have this notation, and now we have our signal x of t represented in terms of cosine and sine functions. Okay, so we call this representation of the signal x of t as the Fourier series in the sine and cosine form. Okay, so it's called the sine-cosine form of the Fourier series. Previously we had seen the exponential form of the Fourier series. Now we have converted it to the sine-cosine form of the Fourier series. Okay, and again, these are the two forms that you will be coming across while solving a lot of problems in this course. So you need to be familiar and comfortable with dealing and representing the signals in both these forms. Okay, so Fourier series in terms of the exponential form, and also in terms of the sine and cosine form. So accordingly, you need to compute just the small ak's, or after computing the small ak's, you'll need to compute the capital AK and capital BK using these relationships. So when trying to obtain the Fourier series representation of a signal x of t, what we have to do is we need to find what is the values of AKs. Okay, and we've seen the formula to compute the AKs, and for different values of k, we need to compute the value of AK, that is for k equal to 0, 1, 2, 3, and so on. And if it's in the exponential form, we directly substitute those AKs into the exponential Fourier series equation, and we get the signal represented as the Fourier series in the exponential form. But if we want it in the sine and cosine form, then we need to compute these capital AK and capital BK terms, and then substitute those values in the sine-cosine form of the Fourier series, which is this equation over here. And that will give us the Fourier series representation of x of t in the sine-cosine form. Now, what we will do is we'll explore a bit more regarding the values of AK, capital AK and capital BK for different conditions. Okay, when we have a real signal, what happens when we have AK and AK to be a real number, and what happens when the signal x of t is a real signal, and so on, right? Under different conditions, we'll see what this representation reduces to. And normally you don't have to, you won't come across, at least in this course, the need to compute the a minus case. Once you compute AK, by knowing the property of the signal, you can calculate what is a minus k. For example, if you know that the signal x of t is a real signal, then a minus k is going to be the complex conjugate of ak. And if it turns out that the ak is a real number, then the a minus k will be equal to the same ak, because a minus k is the complex conjugate of ak, and when ak is real, the complex conjugate is itself. So a minus k will become equal to ak, and so on. Okay, so let's explore that aspect a little bit. So we have these two representations. Okay, I've tried to put everything on one page so that you can see the summary very clearly. So we have this first equation here, which is our Fourier synthesis equation, which is the representation of the signal x of t as a linear combination of complex exponentials, which is called as the exponential Fourier series. And then I've written down again the equation for x of t in terms of the cosine and sine waveforms, which we call this representation or this synthesis equation as the sine-cosine form of the Fourier series. So let me write that down. So this is called as the sine cosine form. Okay, so this representation that we have here, and when we are doing the sine cosine form, after computing the value of small a k and small a sub minus k, we have to compute the capital AK and capital BK values, and once we have all these values, we can find the Fourier series representation either in the exponential form or in the sine cosine form. And the formula to compute the values of the small ak's is given by this integral, and as we discussed earlier, when k equal to 0, this simply becomes equal to computing the average over any one period of the signal. Okay, with a0 is basically the average value of the signal over one period, and that corresponds also to the DC level or DC component of the signal. Now, for real signals, when this signal x of t is a real signal, we said earlier that the Fourier series coefficients ak and a minus k are complex conjugates of each other. So if ak and a minus k are complex conjugates of each other, what happens? That means a sub minus k is ak star and ak is ak a minus k star, right? They are complex conjugates of each other, and when they are complex conjugates of each other, what happens to this capital AK and capital BK? Okay, let's see that, and after that we will wind up today's lecture. So I just taken a simple example here. Okay, let's say our signal x of t is a real signal, and let's say a particular value of ak is 2 plus 3j. Then the value of a minus k, which is the complex conjugate of ak, will become 2 minus 3j. So ak is 2 plus 3j. The complex conjugate of this is 2 minus 3j, and therefore the value of capital AK in the sine cosine form of Fourier series, which is the sum of AK plus A minus K, and so since we have A minus K as the complex conjugate of AK, so once we compute AK, we can find what is A minus K and then add them together and we get a real number. Okay, we get some number here. Okay, so that's our capital AK. And similarly, when we can compute the value of capital BK as j times AK minus small a minus k. So that if you once you evaluate for this example, we get some number. Okay, so what we see is that, what I'm trying to say here is that when you're doing the Fourier series evaluation, you need to compute AK, and from that AK you will usually be able to find the corresponding A minus K value, okay, by knowing the properties of the signal that you're dealing with. For example, in this case, we know that the signal is a real signal. In the case of a real signal, A minus K is the conjugate of AK. So you can directly compute what is A minus K. You don't need to evaluate it all over again. Okay, and once you have evaluated those, you can calculate what is capital AK and capital BK and substitute those values in the series expansion, and you will get the Fourier series representation of the signal. Okay, and if the value of AK is a real number, okay, if the AK itself is a real number, then for that particular AK, the corresponding A minus K will be equal to AK itself. So for example, if this AK is a real number, that means there is no imaginary parts. So that means AK is equal to 2. Then the complex conjugate, which is representing A minus K, is also 2. Right? So A minus K will become equal to AK. And therefore, the capital AK term will become AK plus AK, because A minus K and AK are same, which is 2 times AK. And the capital BK term, which is AK minus A minus K, because they are both same, we get 0 for that. Okay, or what we are saying is that when we have the AKs, if any AK term is real, then the corresponding frequency component, or that particular harmonic, will be represented by the cosine term only. There won't be any sine term in that particular frequency component. As we saw in the earlier example, okay, if you go back to the earlier example that we discussed, we illustrated. So you see here, all the values of AKs we had were real numbers, right? A0 is a real number, A1 and A1 is a real number, and since this is a real signal, A minus 1 is equal to A1, and we get the same value. A2 is half, and since it's a real signal, A minus 2 is the complex conjugate of A2, and since A2 is real, they both are equal. Similarly for A3, right? And when we represented this in the Fourier series, we ended up with only cosine terms. You see, there's cosine 2 pi, cosine 4 pi, and cosine 6 pi. So when the when any AK value is a real number, then that particular term in the series will have only the cosine term. There won't be any sine term in that particular component, in that particular frequency component. So that is just to summarize and quickly give you an idea as to what you're supposed to do when you are computing the Fourier series of a signal. Okay, you will first find the small AKs, and if it's the exponential Fourier series, you just substitute those small AK values in the exponential Fourier series equation, and you get the signal x of t represented as the exponential Fourier series. If it is Fourier series in the sine and cosine form, then we need to compute the capital AK and capital BK terms. And again, the A minus K term can be obtained from the AK term in most of the cases that we will come across in this particular course. So if you remember these points, then a lot of your calculations will become much simpler. You won't even have to calculate, okay, by using the idea and the understanding of the complex numbers and so on. You can evaluate the other terms, and some of the terms will become 0, like in this case BK becomes 0, and therefore your series will become much simpler. Okay, so you don't have to be evaluating each and every term. So if you grasp these ideas, you will be in a better position to solve the problems, and that will save you a lot of time. So it is important that you read and revise these concepts and practice the tutorial problems, and that way you will have a clear idea of exactly what is going on. So we're going to stop here for today, and you'll be doing a lot of example problems in the tutorial section, and I encourage that you practice all the tutorial problems and the tutorial homework that is given to you, because that practice is what will make you comfortable dealing with these problems and being able to solve the problems, and also have a clear understanding of what is the process going on when performing these calculations, and even it will give you an understanding of how exactly the signal is being represented and what information does the Fourier series convey to us. Okay, so we are representing a signal in terms of complex exponentials which are harmonically related, and what does each harmonic component mean, and what is the meaning of each of the Fourier series coefficients, which is what do we mean by these AKs, and so on. Okay, so you need to be quite clear, and these are fundamental concepts, important concepts that you will be using a lot in your future courses as well. So I recommend that you practice the problems and read the textbook also, and get a clear understanding of what exactly is going on when you're doing all these problems, and be clear with the concepts. So we will stop here for today, and later on we'll also be discussing about the Fourier series representation of discrete time signals as well. And what you should bear in mind is that when we talk about Fourier series, we are talking about signals which are periodic. So only Fourier series applies only to periodic signals, whether they are continuous time or discrete time. When you talk about Fourier series, it automatically implies that the signal x of t or x of n is a periodic signal. So finally, to conclude, we make a few, let's make a couple of observations, important observations regarding the Fourier series. The first is that the Fourier series applies to periodic signals, as I stated before. Okay, so whether it is continuous time signals or discrete time signals, when you talk about Fourier series, we're talking about periodic signals. That's the first thing. And the second thing is that the Fourier series, once we have in the frequency domain, Fourier series is a discrete function of frequency. Okay, again, this is an important point that you need to bear in mind. We will discuss in more detail regarding this. Basically, what we are trying to say is that when there is periodicity in the time domain, that means in the frequency domain it is going to be discrete. Again, this is an idea that will be used later when you're studying communication systems in your higher levels. So periodicity in the time domain, let me write that properly. Means discrete in the frequency domain. And the opposite is also true. That means if it is discrete in the time domain, that means the representation would be periodic in the frequency domain. So discrete in time domain means periodic in frequency domain. Okay, these are just observations for the time being, but these are important pieces of information that will be very useful in understanding the relationship between time and frequency domains. Because once when we're dealing with Fourier analysis, whether it is Fourier series or Fourier transform, we are trying to represent the signal, from time domain to frequency domain and vice versa. So you need to have this point in mind, that when something is periodic in the time domain, because we are talking about the signal x of t, which is periodic in the time domain, the x of t or x of n, whether it is continuous or discrete, it is periodic in the time domain, then the Fourier series that we get is a discrete function of frequency. For example, we have omega 0, and omega 1 is 2 times omega 0. Omega 2 is, say, 3 times omega 0 or 5 times omega 0. That means the frequency components have discrete values. It is not a continuous function of frequency. Okay, so when the signal is periodic in the time domain, then it is discrete in the frequency domain. And conversely, discrete, if it is discrete in the time domain, that will correspond to being periodic in the frequency domain. because later on we are going to talk about discrete signals, right? When we talk about discrete Fourier series of the discrete signals, then we will see that that should imply periodicity in the frequency domain, and these ideas would be very helpful in when you're studying other subjects in the future, like communication systems and advanced communication systems and so on. Okay, so this is just some additional points which I added towards the end of this lecture, but nonetheless these are important pieces of information that could be very helpful in understanding certain other topics. Okay, we'll stop here for today, and we will continue in the next lecture, where we'll begin our discussion of the Fourier series as applied to discrete periodic signals.